But Baalbek, if there was one example, one ancient site on Earth that is evidence of a lost, ancient, advanced civilization,
this is the real mystery of Baalbek. How these stones came to be there, why they were placed there, and specifically how they were transported into place.
Baalbek, as we know from the archaeological evidence, must have existed during the Neolithic period, between 6,000 to 8,000 years or even 9,000 years BC.
For years, Baalbek was considered a site historians believed they fully understood. That confidence began to unravel when a new investigation uncovered details that didn't align with any accepted explanation. Researchers working at the site say that the deeper they looked, the more the evidence pushed back. Something about Baalbek simply refused to fit the established narrative. And what they found forced the team to consider a possibility they never expected. It was artificial intelligence that noticed what historians had overlooked. For decades, Baalbek rested on a comfortable assumption. The Romans built everything there. The idea made sense. The Romans had the manpower, the tools, and the engineering expertise. Because the explanation felt solid, historians rarely questioned it. Any inconsistencies were dismissed as measurement errors or simple misinterpretations. That certainty began to fracture when new analyses were introduced. Close examination of the stone surfaces revealed tool marks that didn't match those from the Bronze Age or the Iron Age. More troubling still, they didn't resemble any known tool tradition at all. What had once seemed settled was suddenly wide open again. Repeated physics tests kept reaching the same conclusion. No known ancient transport method could have moved stones weighing hundreds of tons. Roman records offered no mention of any project that involved cutting, lifting, or positioning blocks of that size. Even the orientation of the main platform raised questions, as it aligned with a sky pattern that didn't belong to the Roman period. Some field researchers described the site as a puzzle that could no longer be held together by old assumptions. The contradictions kept piling up until the team realized they needed a completely new approach. That was when they turned to a pattern recognition AI. The system wasn't created for history or mythology. It was originally built for engineering analysis and forensic stone research. The team trained it to detect microscopic traces in metal and stone, interpret ground-penetrating radar data, and compare structural geometry with long-term astronomical models. It had already been tested on Roman bridges, Mayan pyramids, and several ancient Chinese foundations. Internal reports show the researchers trusted the AI for one key reason. It didn't invent theories. It simply analyzed data and measured that data against known construction methods. Before committing to it, the team held several long meetings, debating whether it was time to let a machine re-examine everything from scratch. According to researchers who attended those discussions, they eventually agreed because the traditional explanations were no longer holding up. Once the decision was made, every available file was fed into the system. Toolmark Research supplied thousands of high-resolution scans, hundreds of detailed photographs, and basic chemical readings from the stone surfaces. Geological studies added radar images of the ground below, soil test results, mineral data from nearby quarries, and maps showing stress and pressure points within the bedrock. What emerged next would challenge everything they thought they knew. Every file was uploaded exactly as it had been collected. According to the team, this was the only way to ensure their own expectations didn't shape the outcome. The AI analyzed the data in stages. It compared tool marks against known Old World traditions, assigned probability scores to different construction phases, and built a timeline based on erosion depth and weathering patterns. It also tested the alignment data against every sky model in its database. When the process was complete, the system merged all the results into a single report, highlighting conflicts and unexplained anomalies. The first major contradiction appeared immediately. The massive foundation stones did not align with Roman engineering practices. The AI found no traces of Roman iron chisels and no evidence of Roman proportional systems. Instead, it detected placement methods and load patterns that didn't belong to classical engineering at all. Even the astronomical alignment pointed to a period the Romans never worked with. According to those present during the review, the room fell silent. Some asked for the files to be checked again. Others insisted there had to be an error. But the system was clear. The foundation stones were labelled non-Roman and non-classical. With that conclusion, the accepted story collapsed, forcing the team to confront a far more difficult question. If the Romans didn't cut these stones, then who did? To find answers, the researchers returned to the tool marks, this time fully through the AI's analysis. What followed was even more unsettling. After ruling out Roman involvement, the team approached the stones with renewed urgency, expecting the mystery to finally unravel. Instead, it deepened. The AI showed that the cuts in the limestone didn't resemble marks left by hand tools at all. The surfaces were unusually smooth. The channels followed clean, continuous lines, and the depth of each cut remained nearly identical from start to finish. This level of control didn't match the uneven impacts expected from bronze or iron chisels. Microscopic scans reinforced the concern. They revealed channels that maintained the same width across their entire length, with no signs of hammer strikes or chisel vibration. The AI compared these marks to every known tool pattern in its database: Roman chisels, Phoenician wedges, Assyrian picks, and even Neolithic techniques. None were a match. Then the system flagged something unexpected. Several features closely resembled industrial cutting methods that use flowing water mixed with abrasive material. In these techniques, a steady stream of water guides the cut while hard particles do the grinding. According to unverified accounts from within the team, this was the moment the atmosphere in the room changed. The match wasn't perfect, but it was close enough to raise serious questions. Chemical analysis added another surprise. The AI detected traces of quartz sand and tiny fragments of corundum on the cut surfaces, minerals far harder than limestone and highly effective as abrasives when suspended in water. These materials weren't native to the area, suggesting they had been deliberately brought in. Some researchers believed this pointed to a planned, organized cutting process rather than simple trial and error. None of the traditional explanations could account for this level of preparation. The AI then turned its attention to the quarry floor. It identified signs that the builders had used a freeze and thaw method to extract the stone. According to the analysis, workers would first carve narrow trenches around a block, fill them with water, and allow winter temperatures to freeze it. As the ice expanded, it pressed against the surrounding rock, gradually forcing the block to break free from the bedrock. The system detected distinct vertical cracking and fracture patterns that matched known freeze and thaw signatures. It also highlighted shallow channels cut into the quarry floor that appeared to direct the flow of water. Similar techniques are known from prehistoric Scandinavian sites and early Chinese quarries, but none of those examples were carried out on anything close to the scale seen at Baalbek. When combined, the evidence for water-assisted cutting and freeze-based extraction pointed to a stone working system that didn't belong to any known culture in the region. The Romans had never used such methods, and no ancient Levantine group was known to have employed them either. According to the research team, the marks suggested a process that was precise, methodical, and carefully engineered, signs of a highly skilled and organized group. And that realization made the researchers uneasy. If the stone cutting itself was this advanced, then the challenge of transporting blocks of that size posed an even more troubling question. Transport physics. The cutting methods alone had already shaken the team. But according to several researchers, the real concern began when they turned to the problem of transport. If the stones were shaped using such advanced techniques, then moving them should reveal even deeper clues. The AI was assigned the task immediately. The team still hoped that at least one traditional explanation might survive careful testing. That hope didn't last long. The system began by converting every known factor into usable data. It accounted for the exact weight of each block, the strength limits of wooden rollers, the tensile capacity of ancient ropes, the slope of the terrain, soil friction levels, the contact area beneath each stone, and even weather conditions reconstructed from historical climate records. Internal notes state that the AI was instructed to assume perfect coordination under ideal conditions. The team wanted the test to be fair. They wanted to know whether brute force could work under any scenario. The system ran more than 10,000 simulations. It adjusted roller spacing, altered rope quantities, tested different roller materials, changed route directions, and examined sledges both with and without lubrication. It even explored shallow incline modifications to see whether the ground itself could support the load. The initial results were devastating. Wooden rollers failed almost immediately. Under loads ranging from 800 to 1,600 tons, the rollers flattened, cracked, and shattered. Friction generated so much heat that repeated trials caused temperatures high enough to scorch the wood. The AI noted that even with constant roller replacement, the stones would only move a few inches before the entire system collapsed. Rope-based solutions fared no better. To pull one of the larger blocks, the rope would need to be wider than a human torso. The total weight of the rope alone would exceed that of the workforce required to pull it. Worse still, the tensile strength needed simply did not exist in any known ancient rope-making tradition. According to unverified accounts from inside the lab, disbelief among team members slowly turned into frustration as the numbers filled the screen. Workforce estimates introduced another impossible problem. To generate enough force, more than 30,000 people would need to push or pull a single stone. There was no physical space around the block to place that many individuals. Even if there were, coordinating them would be impossible. The AI labeled the scenario unrealistic. Sledge simulations offered no relief. In nearly every test, the stones sank into the soil. Wetting the ground only increased suction and made the problem worse. With every traditional transport method eliminated, the AI proposed an alternative model. It suggested that the builders created longer but far smoother routes, reshaped the terrain itself, used roller systems arranged in multiple layered configurations, and relied on engineered platforms designed to distribute weight evenly. According to the research team, this level of planning required advanced surveying and engineering knowledge that does not appear in any known culture from the region. At that moment, the researchers understood something critical. Transport was not a matter of strength. It was a matter of design. That realization pushed the investigation in an entirely new direction. Turning toward the sky next, the AI shifted its focus to alignment data. And with that shift, the entire study moved beyond the ground and into the sky. After the transport analysis, the team expected more engineering challenges. Instead, they encountered a question that reached beyond Earth itself. The AI was fed laser measurements, precise sightline orientations, horizon profiles, and solar data. It compared those figures against sky models simulating celestial movement across the past 12,000 years. According to internal logs, the system analyzed solstice sunrises and sunsets, equinox positions, planetary risings, and the slow drift caused by axial precession, the gradual wobble of Earth's axis. Precession completes a full cycle roughly every 26,000 years, and even small shifts can dramatically affect sunrise alignments over long periods. The first step was simple. The AI mapped where the platform pointed relative to the local horizon, then calculated where the sun and bright planets would have risen along that same axis across different eras. Crucially, the system accounted for axial precession, something the Romans never included in their construction methods. According to several researchers, reliable measurement of precession did not exist in classical Roman astronomy. When the AI overlaid the sky models, the result stunned everyone. The platform did align with the summer solstice sunrise, but not during the Roman era. The most precise geometric match appeared thousands of years earlier. The strongest alignment fell roughly between 7,000 and 9,000 years before the Common Era. The team stressed that this dating is preliminary and requires further verification and field validation. Still, the alignment was exact enough to rule out coincidence. That finding forced a complete reframing of the site. If the platform was oriented toward a prehistoric solstice, then its builders possessed a deep understanding of solar geometry, advanced enough to predict sunrise positions centuries, even millennia in advance. To explore this further, the team began comparing Baalbek's results with other deep-time sites known for precise astronomical planning, and the implications were only beginning to unfold. Göbekli Tepe in Anatolia contains ceremonial structures that reflect careful sky observations. Nabta Playa in the Egyptian desert features stone arrangements aligned with solstices. The ancient temples of Malta also point to key solar events. According to some scholars, these sites reveal a shared pattern. Scattered prehistoric groups closely observed the sky and built monuments to mark what they saw. The implication is striking. The Romans did not design Baalbek's foundational platform. Its alignment points to an earlier culture, one capable of modeling the sky over long periods and translating that knowledge into architecture. This level of planning suggests an understanding of horizon geometry, solar movement, and long-term celestial cycles. Several researchers note that such knowledge doesn't fit what we normally expect from late Neolithic or early Bronze Age societies in the Levant. The reaction in the lab ranged from stunned silence to heated debate. Some scientists called for independent verification of the laser measurements and sky models. Others argued that if the alignment held up, then the foundation must predate the Romans by thousands of years. The AI had pushed the team into deeply uncomfortable territory. If the platform belonged to a prehistoric horizon tracking program, then the ground beneath it needed to be examined again. The next step was clear: geological mapping. Geological engineering. That shouldn't exist. The team shifted their focus from the sky back into the earth. After the alignment results, the obvious question became why the builders placed each massive block exactly where it stands. According to field notes, the AI was paired with new ground-penetrating radar surveys and detailed soil analyses. Together, they produced a three-dimensional map of the bedrock beneath the trilithon. What emerged was anything but random. The radar and soil data revealed zones of exceptionally strong bedrock, areas where the rock was fractured or weak, and hidden fault-like cracks running beneath the surface. The AI then overlaid the precise footprint of each 800-ton stone onto this map. The result was immediate and precise. Every single massive block rested on the strongest available bedrock. In several cases, shifting a stone by as little as 4 or 5 feet would have placed it over a weak zone. According to the models, that small change would have caused uneven settling and likely structural failure within centuries. Some team members later said this level of precision seemed impossible without some form of subsurface surveying. The joints between the stones revealed another layer of engineering insight. Laser scans of the contact surfaces showed shapes designed to tighten under pressure as the weight above increased. The stones were cut so that, under load, they locked together. This effect resembles techniques used in modern earthquake-resistant design. It wasn't a simple interlocking system. The geometry redistributed stress in ways that reduced the risk of failure during ground movement. Engineers consulted by the team noted that these joints behaved dynamically under load and were far more sophisticated than basic weight-based fitting. Historically, builders handled heavy loads very differently. And yet, here it was, hidden in plain sight. Japanese pagodas used dynamic joints, but those designs appeared much later in history. Roman builders relied on arches and load relief systems. Egyptian architects depended on sheer mass to withstand pressure. None of these approaches involved selecting bedrock with near-inch precision or shaping joints that actively tighten under weight. Baalbek shows something different. coordinated subsurface engineering, and an understanding of soil mechanics that isn't documented for early societies in the Levant. The implications are unsettling. If the builders surveyed the ground and placed each block with such exacting precision, then they were practicing a form of civil engineering closer to modern methods than to anything we normally associate with the ancient world. They knew how to assess bedrock strength, avoid hidden fractures, and shape joints to manage stress. Some researchers believe this points to organized teams of specialists, people who combined geological knowledge with construction planning. Others urge caution, noting that these conclusions are still preliminary and need further local sampling and independent verification. Even so, the pattern worried the team. The geological choices were clearly intentional, not accidental. They pointed to a carefully planned placement strategy. And if the ground engineering required this level of sophistication, then the stones themselves must have been sized and positioned with equal intent. That realization pushed the investigation to its next breaking point: the stones that should not exist. Once the bedrock was mapped in detail, the sheer scale of the stones became impossible to ignore. Field reports showed that each trilithon block weighed roughly 800 tons and measured about 64 feet long, 14 feet high, and 12 feet thick. These numbers aren't abstract. An 800-ton block equals the combined weight of many heavy vehicles, mass that even modern engineers treat as exceptional. As the figures appeared on the screen, the lab fell silent. Then came the quarry discoveries that made the atmosphere turn colder. One massive block, known as the Stone of the Pregnant Woman, is estimated to weigh around 1,000 tons. It was quarried and nearly fully shaped where it lies, but never moved. According to unverified accounts, the team also revisited a block identified in a 2014 survey that may weigh as much as 1,650 tons. That stone remains exactly where it was cut and abandoned. If those weight estimates are accurate, they go far beyond anything expected for prehistoric megaliths. They exceed published limits by a wide margin. The AI ran the numbers without bias, and the results were brutal. The AI compared the lifting and hauling requirements against what ancient technology could realistically provide. It evaluated crane-like mechanisms, road construction, rope strength, and workforce density. When it came to cranes, the system found no plausible rigging setup available to early societies that could safely lift masses of this size. Road calculations showed that the terrain preparation needed to move such blocks would itself require enormous engineering projects. Rope analysis revealed tensile demands far beyond the limits of known ancient materials. Workforce modelling created yet another dead end. Moving a single stone would require numbers of people that simply could not fit or function around the site. To challenge the findings, modern engineers were brought in. They attempted to design transport solutions using contemporary cranes, multi-axle transport systems, and staged lifting techniques. Even with modern machinery, relocating a 1,650-ton block is a massive undertaking, demanding extensive infrastructure and meticulous planning. Several consulting engineers noted that the size and condition of the quarry stones suggested any ancient solution would have to be fundamentally different from anything recorded in history. That left the team facing stark possibilities. Either an unknown technology once existed at the site, or the builders possessed logistical and engineering capabilities far beyond what has been documented. Some researchers believe this points to a lost technological tradition. Others urge caution, noting that quarry weights can be miscalculated and that the data still needs independent verification. According to internal notes, these debates grew intense. Beyond the technical arguments lay a deeper shock. If prehistoric communities in the Levant were capable of planning and quarrying blocks of this scale, then our timeline of technological progress is deeply flawed. The idea of slow, incremental advancement collapses at Baalbek. These stones demand new explanations, new answers to who conceived them, who shaped them, and how such planning was possible. The team felt the weight of that realization as heavily as the stones themselves press into the earth. With the scale problem now undeniable, the AI moved to its final task. A lost engineering network. The system was instructed to compare Baalbek's engineering fingerprints with those found at other ancient sites. According to internal reports, this step was expected to be routine, perhaps a few minor similarities, nothing more. Instead, the results stunned the room. The AI didn't find isolated matches. It found clusters of shared engineering signatures spread across regions that should have had no contact in deep prehistory. It began with tool marks. The system compared Baalbek's microscopic cutting patterns with samples from Göbekli Tepe, Nabta Playa, early layers at Jericho, the Maltese temples, several Caucasus dolmens, and pre-dynastic foundations in Egypt. The angles, depths, and surface characteristics revealed unexpected similarities. At first, the team suspected an error. The data was checked again, twice. The matches remained. Next came astronomical alignments. The AI tested each site against prehistoric sky models and found that several were aligned with solstice or horizon events dating back to eras before written history. These alignments did not follow Roman or Egyptian conventions. Instead, they corresponded to much older solar cycles. Researchers described the findings as deeply unsettling. It appeared that multiple prehistoric groups had observed the sky with comparable precision. Geological placement added another link. At Baalbek, stones were positioned on the strongest bedrock zones, avoiding weak areas by surprisingly small margins. When the AI examined the other sites, it found similar strategies: placement along stable ridges and careful avoidance of fractured ground. Some researchers argued this could be coincidence. Others pointed out that the pattern repeated too consistently to dismiss. The quarry evidence became the turning point. The AI showed that Baalbek's freeze and thaw extraction signatures closely resembled fracture patterns found at Nobilia and several Caucasus sites. These methods are rare and require a clear understanding of how temperature changes affect stone. Finding matching fracture behavior across distant regions forced the team to reconsider the idea of isolated development. When the system integrated tool marks, astronomical alignments, geological choices, and measurement ratios, one conclusion rose above the rest. According to the AI, these sites may share a single engineering tradition, common methods, shared knowledge, and a consistent way of solving architectural challenges. That would imply communication or cultural continuity long before recognized civilizations emerged. The team emphasized that these interpretations remain speculative and require outside review. Still, the pattern was strong enough that it could not be ignored. The implications were heavy. Baalbek was no longer an isolated mystery. It appeared to be one node in a much larger prehistoric engineering network. That realization raised unsettling questions. If such a network once existed, then an entire civilization or group of cultures may have vanished without leaving written records, tools, or clear historical traces. Knowledge of geology, astronomy, surveying, and stone movement could have been lost completely. Some members of the research team admitted the thought frightened them. If advanced knowledge could disappear once, there is no guarantee it could not disappear again. By the time the investigation concluded, the team understood that Baalbek had done more than challenge history. It had reshaped it. If you enjoyed watching this video, click the cards on the screen.